This is screencast number 3 for chapter 4. Looking back at lesson number 2, I must have gotten carried away with all of the excitement and interesting ideas in that part of the chapter because it went way longer than I had intended. Hopefully this one will be a little bit shorter. In any case, in this particular lesson, we're going to focus in on pH and concentration and acids and bases, particularly as they are used in stoichiometry. And we'll have a number of examples to illustrate this. But first of all, you should remember a little bit about pH from first year chemistry. pH, roughly out of the German, would be sort of a percentage of the hydrogen ions in solution, a very rough interpretation of that, but that's where it comes from. And the reason we have something called pH is because if we were to have a conversation with the general public about how concentrated an acid or a base solution might be, to use numbers such as the number right here, let me get in red, where you have 10 to the minus 3, and you've got this letter M having to do with molarity, those ideas are quite difficult for most people to understand. Either that or they long since forgotten what these ideas meant from high school because they just never have used them in their everyday life. And because acid and base solutions are so common in the environment, we can talk about the atmosphere, we can talk about rain, we can talk about beverages, we can talk about oceans and rivers and lakes, we can talk about all kinds of solutions that can be acidic or basic. The interest and the need to understand the acidity or basicity of this solution is very common and very important. So by having this thing called pH, we can take this wide range of possible acid and base strength solutions and express it pretty conveniently in a number scale that goes basically from 0 to 14. And where those numbers 0 through 14 come from, you can see the derivation of this mathematically on a separate handout that should be on Canvas. And in a nutshell, the idea is that if you begin with the recognition that the purest of pure water that we can possibly make, without any contaminants that we can basically measure, still yields a very, very, very minute electrical current when you pass electricity through it. And the reason is due to the auto-ionization of water molecules. About 2 water molecules out of every billion are going to do this: break up into a hydrogen ion and a hydroxide ion. And the presence of those charged particles, because those would be mobile charged particles, would allow even the purest of water to conduct some electricity, though it would be very, very difficult to measure that. And when you begin with 2 out of a billion, you actually can end up with seeing a range of values from 0 to 14. Now, I should also say that despite what it says right here, that defining pH as a negative log of the hydronium ion concentration produces a positive number, theoretically you could get a negative number. We know if you have a solution that's 10 to the minus 1 molarity, the pH is going to be 10 to the negative 1. The pH is going to equal 1. And if you have a more concentrated solution of 10 to the 0 molarity, you could get a pH that equals 0. Now, that would be a very, very high concentration of hydronium ions, but that might be possible at a very high temperature of water. And if we even had a higher temperature of water and somehow managed to get a concentration of 10 ions per liter, then your pH would actually be a negative 1. And the purpose of this negative sign here is to get rid of these negative exponents, like there and like there. Negative numbers are rather confusing when you're having conversations with the general public about the strength of a acid or base solution, whether it be in the environment or the human blood or in a beverage. The logarithm allows us to express these wide ranges of possible concentrations and narrow it down. So we use the logarithmic scale. Remember, any number can be expressed as 10 to some power. So if we have 1, we can express that as 10 to the 0 power. If we have 10, we can express that as 10 to the 1 power. But if we had a 2, that number can be expressed as 10 to some fraction up here. You'd have a fraction in that number. So any number can be expressed as 10 to some power. And some examples of the pH of some solutions are given right here. And notice that typically when we talk about pH, we use 25 degrees Celsius. And that's a good reminder that except when we're talking about gases, where our standard temperature is considered to be 0 Celsius, or 273 Kelvin. Every other place in chemistry, we use 25 degrees Celsius. And I think I've come across a few textbooks over the years, and maybe in other countries that might use 20 degrees Celsius as standard temperature. So you can get slightly different values depending upon your textbook and what country the textbook was made in, and when that textbook was made as far as these values for pH. So moving right along, we often like to use red for acidic solutions at one end of a spectrum and blue for basic solutions. It's nice that blue and base both begin with the letter B, and that's how also we think about litmus paper. Litmus paper is a kind of paper that is going to turn blue in a base, BB. And blue litmus paper will turn red in an acid. And the red and acid both end in the letter D if you need a new mnemonic device to help you to remember this. And that would be common knowledge. That would be expected of you to remember on an AP test or a college level test. And there are many other kinds of pH papers besides litmus paper. And by the way, you might wonder, where does the word litmus come from? Litmus actually comes out of the Scandinavian languages, the Norse language, think of the Vikings. And it comes from two different words. The first part of the word we would translate as dye, D-Y-E, and the second part of the word we would translate as moss. And the long time ago in the Norse language, the idea was that if you took this moss-like substance, and it technically isn't moss, it's actually a lichen, and that often grows on rocks and sides of trees and so forth. It isn't really moss. It is a combination of two organisms, fungus and algae, that live in a mutualistic relationship. And the fungus is what provides some structure and protein and scaffolding for the algae. The algae provides the photosynthesis and the food. The fungus supplies the ability to withstand tough environments and to live on rocks and so forth. And the two organisms together form this thing that we call lichen. And there are certain lichens that when you grind them up, you can extract the dye. So it really isn't a moss. It's a mutualistic or symbiotic relationship between organisms. But from that ground up lichen, we can embed it in paper, and it'll turn red in an acid and turn blue in a base. And you should know how to go from pH to hydronium ion concentration and from hydronium ion concentration to base. You should be able to do the math going in either direction. And there's a handout for that as well. This is all review, which is why I'm not going to break that down any further. The other thing you should make sure you know how to do is how to go in either direction with your calculator. I will say that if we are trying to find the hydronium ion concentration of something, and let's say we get 10 to the negative 2.7 or something like that, you can't leave it like that. You have to turn this whole form into 10 to some whole number power. And of course, that's going to require you to have some numbers out front in order to express your hydronium ion concentration correctly when you're given a pH of 2.7 in my illustration here. So make sure you know how to use your calculators. Now, different calculators do this in different ways, and most of you will have a TI 84 or something like that. But if your battery runs out and you're forced to use a different calculator, like one that I would have in a box as backup for students, make sure you know how to find your logarithm from the hydronium or the hydronium ion concentration from the logarithm, regardless of what calculator you're going to be using. And we also are going to be using pH probes. They used to be extraordinarily expensive, and it was difficult to do many labs when I first began teaching because of the cost of getting decent pH readouts. But nowadays we have probes that attach to our lab quests, and it's much more economical. That's not to say that these pH probes that are connected to the lab quest aren't expensive. They can be over $100 each, and they're also rather fragile. Another way in which to find the pH of something is to grind up some red cabbage. If you find some red, it's actually purple cabbage. It looks more purple to me anyway. And you were to say chop it up and boil it in boiling water and take the solution, you can get a nice full range of colors in acidic and basic solutions without having to depend on litmus paper or a pH probe. pH probes, of course, are going to give you readings to the 10th and the hundredths place. And of course, that hundredths place isn't going to be very stable because just the subtle changes in temperature and the subtle movement of the particles in solution will probably cause that hundredths place number to dance around a little bit. Not only that, but in a solution that's open to the air, oftentimes you're going to get some carbon dioxide that's going to go in there, and that's also going to affect the pH readout, especially in the hundredths place and maybe even the tenths place if you leave it sitting out long enough. So the idea is you put your pH probe into the solution and let this reading here settle for 5 or 10 seconds, and then just take that reading, and that should be good enough to get the job done. Now, obviously, you already know that there are strong acids and there are strong bases, and hopefully you've memorized them, the 6 strong acids and the 5 or 6, depending on the textbook, strong bases, and all the rest are weak acids and weak bases. And what you should also know then is that if I had a 10th molar solution, let's say of a strong acid, I can be very confident that the pH of that solution is going to be 1, because the negative log of 10 to the minus 1 is going to equal the exponent, minus 1. But if I have a weak base, let's say a weak acid, let's say I have a 10th molar solution of acetic acid, and I'll be writing it like an inorganic chemist. You could, of course, write it as an organic chemist, CH3CH2OH. This hydrogen and this hydrogen doing the same thing. And I forgot to stick an O in here, COOH. Let's see. that gets rid of that. There we go. Got to get that correct. So I'll write it again, CH3COOH. There we go. This is the hydrogen that will be donated. This proton will be donated as a Bronsted-Lowry acid. And here, if I had a 10th molar of this solution, the pH most definitely is not 1, but the pH is going to be greater than 1, meaning that the pH is going to be not as acidic, because remember, the lower the number as you approach 0, you become more acidic. In fact, the pH is more likely to be somewhere like around 2.7 or something like that, depending on the temperature. And in this particular problem, we're not going to go over this example, but you're finding the pH of a hydronium ion solution. Or if you're given the pH, you're working backwards to find the hydronium ion concentration. And here, of course, if you have a strong acid like nitric acid, your pH is going to be and let's come down here, your pH is going to be the negative log of the molarity of the acid. Because it's a strong acid, the pH is the negative log of the molarity. So it's 10 to the negative constant molarity. And coming over here, stoichiometry of reactions in aqueous solutions. So what if we're asked this question: what mass of calcium carbonate is required to react completely with 25 mils of 0.750 molar HCl? Now you should remember that 99 times out of 100, and I'm making that number up, but almost every time you see a volume and a molarity, you're probably going to be multiplying those two numbers together in your calculation. And so we are given this information about the hydrochloric acid, and we're going to convert this into moles, and then we're going to go from moles to moles of calcium carbonate, and then from moles of calcium carbonate to grams of calcium carbonate. So we're basically going to have a 3-step stoichiometric process here. And in this case, instead of being given grams of hydrochloric acid and having to convert it into moles, we're just going to multiply the volume times the molarity together. So here is my volume converted to liters, and here is my molarity, moles per liter. And when I multiply the volume times the molarity together, I get my moles of hydrochloric acid. Remember, in this textbook, they often use the letter C for concentration instead of the capital letter M for molarity. The letter capital, the lowercase c would be a little more generic because you can have other concentrations besides molarity, but molarity is the most common. So that takes care of step number 1 right there. Then I'm going to do the stoich part. The stoich part is right here. And you can see that I have a 2-to-1 ratio. And make sure you have the 2 in the denominator, not in the numerator. And that's where setting up a dimensional analysis problem helps you to cancel out the moles of hydrochloric acid, leaving the moles of calcium carbonate. And of course, calcium carbonate is a solid. You can see that there. So we're going to convert it into grams, like always. And you would combine these steps for sure in one dimensional analysis problem. This is step 3, step 3. And here's a road map. And typically we go from grams to moles, moles to moles in the stoich step, and moles back to grams. But in the illustration I just did, we took our volume times molarity to get our moles, and then from moles to moles, and then we can go from, we can find volume or molarity back again, or we can go up this way. So there's lots of different ways, depending on the problem, you can use this schematic. And I don't find that necessarily worth memorizing, because if you just let the dimensional analysis do your work for you, and remember that VM is a way of expressing the number of moles of a solution, Remember, volume times molarity equals moles. You should be good to go. Here's another problem. What volume of 2.50 molar hydrochloric acid is required to convert 11.8 grams of zinc completely to products? So that must mean that zinc is my limiting reactant, and therefore I have more than enough hydrochloric acid to entirely react with it. And my roadmap looks like this. I'm going to go from grams to moles. And then we're trying to react this with hydrochloric acid. So I'm going to do stoichiometry to get my moles of hydrochloric acid. And then once I have my moles of hydrochloric acid, since I know the molarity and I'm going to know the moles, and we know that molarity equals moles per liter of solution, I'm given the molarity. I'm going to calculate the moles right there, and I can solve for the liters. And once I solve for the liters, I can convert it into milliliters as the problem asks us to do. And so when I do these steps, in terms of my roadmap, the first roadmap right here, first step is to go from grams to moles. And then the second step is to do the stoichiometry right here, moles to moles, and I would do those in one dimensional analysis problem. And then once you find your moles of hydrochloric acid, and you have your, you can solve for your overall liters of solution by getting the moles to cancel out. And because you're given the 2.50 moles per liter. Notice now that my moles per liter is upside down in order to get the moles of hydrochloric acid to cancel out. So sometimes when you're given a piece of information like this, you're going to take the reciprocal of that in your dimensional analysis problem. Now, titrations. You've done a few titrations, if I remember correctly, in your first year chemistry class. Hopefully you remember that a titration is a way of finding that moment, that point where your moles of hydronium ions equals your moles of hydroxide ions. In other words, Vm equals moles, and in this case it would be moles of the hydroniums in your acid, and then you have your Vm or moles of hydroxide ions in your base. And when these two equal each other, you're at the equivalence point. Because if you think of the word equivalence, EQUI, equal, and then valence. Remember, valence has to do with those electrons in the outer shell. When the number of electrons gained is equal to the number of electrons lost, that would be in a redox reaction. But in this case, we can think of charges. When your positive charges from the hydroniums equal the negative charges in the hydroxides, then you're at the equivalence point. Now, a little caution here. Sometimes you might have a diprotic acid. Like right here, you have a diprotic acid. You could also have a diprotic base. For example, calcium hydroxide with a subscript of 2. So sometimes you're going to need to put a 2 here or a 2 there if the acid is diprotic and the base is not, or if the base is diprotic and the acid is not. So that's a little different than when we talked about Vm equals Vm, the equation we used when we were talking about, if you remember in the last screencast, which was way too long. Here we had, and we were taking our concentrate and we were diluting it. In that use of Vm equals Vm, you don't have to worry about having a coefficient. So make sure you are aware of that. Always got to be on your toes. Now, in this particular acid, we're going to be taking oxalic acid, and we're going to be, which is a solid, by the way, it's going to be dissolved in water. And it actually doesn't matter how much water you dissolve it in, because the amount of oxalic acid in the solution is going to be the same whether you're using a little bit of water or a lot of water. Think back to the illustration of having 10 girls in the classroom and some more boys walk in. It doesn't matter how many boys walk in, you still have 10 girls in the classroom. That doesn't change, even when you dilute the concentration of girls in the room, so to speak. So in this, this is the balanced equation because we're using a diprotic acid and a monoprotic base. And of course, we're always going to get the same thing, a salt and water. And this reaction is going to go to the right because you're making liquid water with its strong bond between the hydrogen and the hydroxide. So even though I'm using a weak acid, it is going to go to the right. Now, let's come up here, and hopefully this looks familiar. We are using a burette, and this burette is pictured attached to a burette clamp on a ring stand. Here is the valve or the stopcock, and it's got a little handle right there that you rotate when the handle is parallel to your pipette, your burette. That means the liquid can fall into the flask. When the handle is perpendicular, that's the off position. And the same is true if you ever have to turn the gas on or off, let's say to the master valve in a room like we have in the chemistry lab, or the master valve of natural gas coming into your house. And as we add the solution, in this picture down here, as the solution is going in, periodically you will see flashes of pink because of the fact that the acid hasn't been thoroughly distributed yet, or I should say the base in this case, because we have sodium hydroxide up here and we have our oxalic acid, which is down here in solution. And so if you haven't stirred it, or if you haven't swirled the flask around yet, and if you haven't rinsed off the sides of the flask with water to make sure that there's no sodium hydroxide sticking to the sides, you could have places where it's temporarily pink, and you have to thoroughly mix it. And then if you keep it thoroughly mixed, there'll be some point at which one single drop of base will turn the solution pink, and it'll stay pink. And it'll be a very, very light pink, not a dark pink. And that's when you have correctly titrated your sodium hydroxide against your oxalic acid that is in solution. And the equivalence point, of course, means equal charges. Now, if we look at this next example, notice that you're given both a volume and a molarity, so you can expect to be multiplying those two numbers together. Notice that this is in milliliters. And by the way, if you are using Vm equals Vm with an acid against a base, you can leave your volume in milliliters, which means your other volume is going to be in milliliters as well, just so that you're consistent. And so let's take a look at this problem. And by the way, the structural formula here, notice that we have a hydroxyl group there and a hydroxyl group there in the oxalic acid. And there's my two protons. As you titrate, you're going to remove the first proton from every single hydroxide oxalic acid molecule. You'll remove the first proton. But then if you keep adding sodium hydroxide and go past the first equivalence point, then you're going to start knocking off the second proton, titrating off the second proton. So that does change the shape of your titration curve. So if we do this particular example, and by the way, in this particular example, this is actually the kind of thing that's going on in Lab 6. In Lab 6, if I remember the number correctly, you are actually going to be using oxalic acid to standardize the sodium hydroxide base in your burette. And then in lab 7, you're going to take that standardized sodium hydroxide base, whose molarity you have carefully determined in lab 6, and you're going to use that to determine the molarity of two unknown acids, one of which will be a strong acid, one of which will be a weak acid. And that's in lab 7. So we will do labs 6 and 7 back to back and take an entire week in order to do that. So in this particular math problem, which is also lab 6, you can see the flow chart or the schematic diagram of what you'll be doing over here. It is summarized in these bullet points, which I've numbered right here. And they're doing the dimensional analysis, but they take it apart rather than combining the steps, which I think, as you are familiar with this process, you ought to do. And so here's my oxalic acid, which is my weak acid. There's my strong base. Here's my strongly soluble salt, sodium acetate. And then here's the reason the reaction is going to the right, which is water. So you write your balanced equation is in step 1. In step number 2, you're going to be multiplying your molarity. This is your molarity. They use the letter C for concentration, times your volume. There's your molarity times your volume to get your moles. So that's what's done right here. In step 2, you're getting your moles of sodium hydroxide solution. I think I put my arrow in the wrong place. So let's just take care of that. And we'll go ahead and erase that. So we're going to take our molarity times volume to get my moles. And that's my step number 2. And then the next part we're going to do is the stoichiometry. And of course, this is a 1 oxalic acid to 2 sodium hydroxide, 1 to 2 molar ratio. That's step number 3, which is right down here. Notice you're dividing by 2 because you're going from the 2 to the 1, which is in front of the oxalic acid. And then the next thing that you're going to do is you're going to convert your moles up here to grams. And that is going to be step number 4, right here, step number 4. And once you have your grams of oxalic acid, you can divide it by the impure amount given to you in the problem. So we're not using we have impurities in our oxalic acid. The sodium hydroxide only reacts with the oxalic acid. And so we can calculate our percentage of purity of oxalic acid in this sample by dividing the pure by the overall sample. And now we found the purity of oxalic acid. And like I said, this is something that you're going to be doing in lab 6, but in actuality, your oxalic acid is going to be purchased from a chemical supply company, and it'll be pure. So we won't have to find the percentage of oxalic acid in an original sample that we've massed out. We're just going to mass out the oxalic acid directly, and with that we get our moles of oxalic acid as we go to standardize our base, which means we're going in the opposite direction of the problem that right above that we just completed. That's what we mean by standardization. 2 ways to do this. We can do this in the laboratory by buying a very, very pure sample of my primary standard. For example, in lab 6, it's going to be the oxalic acid, and we're going to standardize our sodium hydroxide base, which we'll need in lab 7. Or that's the other thing we can do is we can actually titrate it against another solution that is standardized. In fact, this is more what we're going to be doing in Lab 7. So if we look at this standardizing an acid by titration, if we standardize, if we have sodium carbonate is our base, and we mass out very carefully, and this is why we have to use our analytical balances. Our analytical balances can go to not just 0.01 grams, which you're used to in first year chemistry, but 0.001, the thousandth of a gram. And then we have some $2,000 analytical scales that can go 0.0001 grams. And these are in the fume hood and are very, very delicate. And we can get very, very precise mass readings because we want our titrations to be as accurate as we can possibly make them. And once again, you can see step number 1, we're going to balance our equation. And so here we have a salt, sodium carbonate, but you might recognize that the sodium, and I'll use language that we'll use again second semester, but sodium is the conjugate acid of a strong base. It comes from a strong base, for example, sodium hydroxide. And so therefore, we have the sodium part is from a strong base. The carbonate part is from the weak acid, carbonic acid. If we were to make sodium carbonate directly, and this is a weak acid, and since we have a strong base and weak acid, sodium carbonate is not neutral in solution, but would have a basic solution. You might not remember the conjugate acid of a strong base versus the conjugate base of a weak acid, but we'll be reviewing that in a later chapter. In any case, my sodium carbonate is acting like a base. Hydrochloric acid is acting like an acid. I'm going to get my salt, sodium chloride, in water. And these are the reasons this reaction is going to go to the right. Because we take our carbonic acid, which is formed, and this further decomposes into water and carbon dioxide. So the second thing we're going to do after writing our balanced equation is we're going to go from grams to moles of sodium carbonate. So we're going to go from, let's erase some of this stuff here. So we are going to go from grams of sodium carbonate to moles of sodium carbonate. Then we're going to go from moles to moles of acid. And that's the stoichiometric part. So here is step 2 is right there. Step 2 is right there. Step 3 is in that arrow, which is down here. Step 3. Notice it's a 2-to-1 ratio. Notice that my 2 is in the numerator this time because we're going from left to right, from a coefficient of 1 to a coefficient of 2. And now I have my moles of hydrochloric acid, and we don't want grams of hydrochloric acid. What we want is molarity of hydrochloric acid. So I take my moles of hydrochloric acid and divide it by the volume to get my molarity of HCl. Determining molar mass by titration. And remember, molar mass is very important because it's actually the identity of a compound. If you find the molar mass of something, you basically know what compound it is, because very, very few compounds, different compounds have exactly the same molar mass. So 99.9 times out of 100, the molar mass of something is unique to that compound, and you have identified it. You might also remember that the empirical formula is the simplest whole number ratio, and we want the molecular formula, which is the actual molecule and structure as we see it in the solution. So we're going to, in this particular problem, we're going to be determining the molar mass, and we're going to be of an acid by titration. We're going to be using titration to find the molar mass of an organic acid. Now, if it's an organic acid, it's going to be a weak acid, because if you might remember that your strong acids, all of them are inorganic, like HCl, HNO3, H2SO4, HI, HBr, and then your perchloric acid. All of these acids are inorganic acids. So by definition, an organic acid is going to be a weak acid. If you're walking down the street and you're accosted by Al Qaeda and they give you the name of an acid and it's an organic acid, you can tell them with absolute confidence that it's a weak acid and not a strong acid. And then you can live to confront them another day. Now, one of the ways to write an acid's formula generically, don't laugh at this, is HA, haha. And the H, of course, is the proton that's going to be donated, and A can stand for anion, like the acetate or the chloride or the nitrate or the sulfate or whatever. And the A is also going to be the conjugate base of the weak acid, or the conjugate base of the strong acid, depending on what acid you're given. So here's my acid, here's my base. We're going to get a salt. And again, the A here is my anion, where the sodium is the cation in the salt. And here's the driving force of the reaction, which is that water. So when we go to do this problem, we're going to first of all go from multiply our molarity. There's my molarity times my volume, V, the MV in this case. And again, your textbook often uses the lowercase c for concentration. Now I have my moles of sodium hydroxide. And then I do my stoichiometric ratio, and we get a 1-to-1 ratio. So now I have my moles of my weak acid right here. And then when I take my moles of weak acid, I can convert it into grams. I'm given the grams of my weak acid in the original problem. Organic acids are often solid, like oxalic acid, for example. And so if I'm given this in the problem and I've just calculated my moles of weak acid, then I just simply divide the one into the other to get the molar mass, 122 grams per mole. That is its molar mass. And if you experiment around with some of the weak acids, or actually you could probably look it up on, Google it, and look it up on the internet and find out which acid has a molar mass of 122. Because there probably is only one. And in this case, it actually happens to be citric acid. Kind of acid in lemon juice and many sodas, limes and grapefruits and oranges and so forth. Another kind of titration we can do is oxidation reduction, or redox titrations. And here we're going to be focusing on the transfer of protons. And in this particular problem, you're given the net ionic equation. The spectator ions have already been canceled out. My bet is potassium is one of the spectator ions right here. Potassium permanganate was the original substance, and probably iron nitrate was where the iron came from, and also helped to produce the hydroniums in the acid solution. And the potassium and the nitrates have been canceled out, and we get the manganese ion right here, +2. Check it out in the periodic table. And then our iron 3 ion right there. And then we need a bunch of water molecules to balance out both the charge and the atoms and the electrons being transferred in this reaction. And again, balancing redox reactions is kind of complicated, and there are examples in one of the screencasts if you need to go back and review that. Now in this problem, you'll notice again, we're given both the volume, it's in milliliters by the way, and molarity. So you know we're going to be multiplying these two values together. Now before we continue the problem, as long as we've got the picture here, as you know, oceans have salt water, and you might say, well, where are the salts coming from? Well, the salts are being formed from two places. You're going to have carbon dioxide in the atmosphere that's going to combine with the water and also combine with rain. Rainwater is slightly acidic. We used to have some places because of lots of pollution back in the 50s and 60s in particular, where we created acid rain. And by that we meant not just ordinary rain, which is naturally acidic from ordinary amounts of carbon dioxide, but really, really acidic acid, because the water was picking up sulfates and sulfites and sulfides and nitrates and nitrates and nitrides and all kinds of stuff. And the rainwater was very acidic. It was really corroding things made out of metal, like bridges and some buildings and the chassis of cars and so forth, and doing an awful lot of damage, not to mention the ecological damage of killing sensitive aqueous environments and the microorganisms and the flora and fauna that live in those water environments. Now our air is remarkably clean for the most part in this country. We do have some pollution problems by major cities that might be where the movement of air is a bit trapped by mountain ranges. You see this in Los Angeles and Mexico City. You see this in some major cities in China and Japan. But in any case, if the rain, you're going to get slightly acidic rainwater, and that slightly acidic rainwater is going to create bicarbonate and calcium ions, and you're also going to get erosion. And as rain erodes away land and comes down rivers and so forth, you're going to pick up a lot of ions of sodium and aluminum and potassium and other kinds of ions in much, much smaller quantities. And so you're going to have all of these ions in ocean water. Ocean water is going to be a conductor of electricity because it'll be a much, much better electrolyte than the relatively pure water of natural rain, like natural rainwater is relatively pure. And we might want to know, what is the chloride ion concentration in seawater? And what are the concentration of the other ions? Now, a whole lot of ions primarily comes from volcanoes. And there are always volcanoes erupting. Recently, we've just had Mount Kilauea, I think in Hawaii, erupting again. There's usually a mountain over in Indonesia, one or two that are erupting. Occasionally, you might have one in the around the Ring of Fire, like around Italy. So we get a lot of chlorine ions from volcanic action. In fact, this would be a natural pollution. And there are times where you're getting so much eruption from these volcanoes that airplanes can't even fly through the plumes of the pollution, the natural pollution coming from these volcanoes, because it would foul up their jet intake engines, the air intake in the jet engines. In any case, these ions are going to dissolve in the ocean water. And the ocean water chemistry is so complicated that ocean water is like a huge buffer that is able to absorb hydrogen ions and to make salts or release hydrogen ions. It can absorb tremendous amounts of carbon dioxide or release carbon dioxide, as the case may be, depending upon the stress in the equilibrium of the ocean water. Remember Le Chatelier's principle. God designed a planet with 3/4 of the surface of which is covered with ocean water that's going to act as a buffer to changes in our atmosphere and changes in the runoff from oceans, and maintain a relatively constant pH. So that's pretty remarkable. And we could use the Moore method, which we talked about in a previous screencast, to try to find out the concentration of ions in ocean water. For example, in this case, we can find the concentration of chloride ions by titrating it against a standard silver nitrate solution, because it'll make a solid of silver chloride, which we can precipitate out. So back to our redox reaction, which I introduced a moment ago. Let's take a look at the steps here. After we write the balanced equation, we are going to do what I've said many times now. We're going to multiply the molarity times the volume together in order to get our moles of the permanganate ion. And then once we have our moles of the permanganate ion, which would also be our moles of potassium ions, which are spectators, then we do our stoichiometry part. We have a 5-to-1 ratio. We're going to get 5 ions for every 1 permanganate ion. Check the balanced equation that you can see that. So now I have my moles of my iron 2+ ions. And then down, and I guess that's where they end their calculation. But once we get those iron ions, that produces a color change, which is why we would be using potassium permanganate in this titration instead of your typical indicator. Oh, here are the other steps. Step number 4, we're going to take our iron ions, and you'll notice we can convert that into grams. And then once we have our grams of iron +2 ion, if our original sample, which is given in the problem, is this, and we know that we have a little more than 10 times this number, 1/10 of this amount of mass of iron ions in my sample, you can see that this is a 12.9% iron 2 concentration in this sample. So we can use this method, for example, to analyze the iron content that might be in a iron fortified beverage, or might be in in ocean or lake or river water, or might be in an iron ore sample that we've dug out of the ground and we put it into solution, and we're using the potassium permanganate in order to find out whether or not it's a high enough concentration of iron to go to the trouble of mining it. But this is based upon the number of protons being lost to equal the number of protons being gained. You also have electrons being exchanged, and all of which must be balanced in this redox reaction.